So I'm making this video to recap the lesson. Hopefully it'll help anybody that needs to review what we went over the last couple days on hybridization. So the learning objective is on the screen. So we want to know how hybridization helps us understand the bonding that occurs in molecules. So before we got into this lesson, I went over valence bond theory with you, where it says if you have unpaired electrons in orbitals, so we use the example of hydrogen and hydrogen, then those orbitals can overlap. And when they overlap, they can form bonds. This is called a covalent bond. So I shared another example, and a few more than this, but I'll show you one more, where we have an s orbital from a hydrogen that's unpaired, because hydrogen only has one electron, and then an unpaired electron in one of fluorine's p orbital. So they can also overlap. And this is called a bond. This molecule is hydrogen fluoride. Now these are examples of head-on overlap of atomic orbitals. So they're known as sigma bonds. Sigma bonds, denoted here with the Greek symbol sigma. So sigma bonds are the head-on overlap of atomic orbitals. Okay. Now you might be wondering, how else are bonds formed other than head-on overlapping? Well, there's another way that happens side to side, so we'll cover that later in this lesson. So before we start, we need to understand what the problem is. Like, why even learn this? Why is this necessary? In reality, we know that there are molecules that have bond angles of 109 degrees, 109.5, right? And one example is methane. Methane forms bond angles that are 109.5 degrees. We also know of molecules that form bond angles of 120 degrees. These are all 120. These are all 109.5. And we call this geometry trigonal planar. And the example we used in class was ethylene, C2H4. We also know that there are molecules that have a linear geometry around a central atom. In other words, they have bond angles of 180 degrees. And the example we used in class was ethine. Why is this a problem? Because up to this point, we only learned of these shapes. They're not really discrete shapes, they're regions of probability, you know this. But we only learned that in an atom, there's an s orbital, there are 3 p orbitals, there are d orbitals too, but we only talk about s's and p's in this lesson. So this is a ball looking thing, a sphere, and you have 3 of these dumbbell things, and they're fixed. Well, they're not fixed, but their positions are along the x-axis, the y-axis, and the z-axis. In other words, they're all 90 degrees away from each other. They're all perpendicular. They're all at right angles. If we're only restricted to using these atomic orbitals, we're only able to get molecules with bond angles of 90 degrees. Unless it's a hydrogen, because then you can have an s overlap with an s, and then you just have like a stick-looking thing. That's the problem. We can't get 109.5. We can't get 120, and we can't get 180 degrees. And there's other angles, or many other angles, but we can't get any of that if this is all we have to work with. So we have to adjust our models, and we have to include what's called hybridization. Here are the steps to determine what the hybridization of an atom is in a molecule. First, draw the Lewis structure. Then, use VSEPR to determine the electron pair geometry, or the effective pair, or the electron domain geometry, not the molecular geometry. Use those bond angles and that'll tell you how many orbitals you need to mix. That's called hybridization. So let's first consider methane. Again, first step, draw the Lewis structure. If you draw the Lewis structure, you get this. Follow your steps. I'm not going to go over that in this lesson. Number 2, use VSEPR to determine the geometry around the central carbon. 1, 2, 3, 4 regions of electron density. That's going to tell you these angles are 109.5. In other words, it's tetrahedral. Okay, that means we need 4 equivalent orbitals to make these bonds. If you look at an unhybridized carbon, the valence shell looks like this. It has 2 electrons in the 2s orbitals, orbital, and it has 2 electrons in its 2p orbitals. Again, you can't have a ball and 3 sticks and get 109.5 degree bond angles. So we need to mix all 4 of these. There's the key. When you need 4 orbitals to make those angles, you need to mix 4 atomic orbitals. Once you put that in the blender, they will all come out exactly the same looking. Now, since you mixed 1 of the s's and 3 of the p's to get these 4 hybrid orbitals, we call each of these sp3 hybrid orbitals. If you want to put a 1 there above the s, good for you. Now, we're going to use this hybrid scheme to describe the carbon. Let's see what that looks like. We got carbon in the center, and it's got 4 of these sp3 hybrid orbitals. It doesn't have any more p's, doesn't have any more s's. It just has 4 of these that replaced its original atomic orbitals. I'll do the 4 hydrogens in blue. They're a little bit lower in energy, and they each have 1 electron they're bringing to the molecule, and it's in the 1s orbital. Oh, I forgot to fill the carbon with its 4 valence electrons. Let's see what this looks like. This orbital I'm going to draw left to right here. That orbital, okay, here's the carbon, let's say. Here's that one right there. All right, by the way, if you mix an S and a P, you get something that looks like that. All right, and we often don't, yeah, that's just what it looks like. All of these hybrid orbitals look pretty much the same. They look like that. All right, so there's that one. And we're going to overlap that with that H bond. All right, so there's an electron in there, and now here comes the hydrogen with this 1s orbital electron. And there's an overlap, there's a sigma bond. Okay, now all right, we've done those 2. Now let's do these 2. Let's bond these 2 orbitals. All right, we can put them 109 degrees. That's a little more than 109 degrees, because we have 4 of them and nothing else. There's carbon's valence electron right there. Now that's coming to meet with hydrogen's electron right there, and hydrogen brings in an s orbital. Right, I'll label these H's. All right, now we have another one coming out of the screen at you. Okay, let's say that's that one. Okay, we're here now. That's going to form a sigma bond with that hydrogen now. Going to need a little bit more room. This is coming out at you. Right, and there's the hydrogen right there. Finally, we have a sp3 orbital, hybrid orbital, going kind of behind the screen. And there's an electron there, and that's going to overlap with this hydrogen. Right, so here with there. So there's your methane molecule. We can now describe it, because once we hybridize these orbitals, we can get these bond angles of 109.5 degrees tetrahedral. right? So when you need bond angles of 109.5, the answer is sp3 hybridization. That's what's going on with that carbon in order to make these out. All right, scenario number 2. We looked at C2H4. Step 1, draw the Lewis structure. So if you follow the rules on making Lewis structures, you get something like this. Step 2. Now on your test, we'll specify, if there's multiple atoms that are essential, we'll specify which one we want you to determine hybridization on. So let's say, just first, they're both the same. Both of those carbons are the same hybridization. Let's say I pick this one on the left. Right, so you want to, after you draw your Lewis structure, determine the VSEPR geometry of the electron domains. There's one, that's one here, that's one effective pair. Those bonds are not independent of each other, they can't separate. That's one region there. There's a second region there, there's a third region there. When you have 3 regions of electron density, this is known as trigonal planar. The bond angles here, 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 and the same thing over here, here, they're all 120 degrees. All right. Anyway, you just need to focus on the central atom we tell you to. 120. If you need 3 equivalent bonds, which you do, to get 120, that means you need 3 equal orbitals to participate in those bonds. Okay, let's do it. So here again is carbon's unhybridized electron configuration. I'm just doing the valence electrons. 2 in this 2s. And then 2 more in the 2p sublevel. These are what carbon brings to them as a regular atom before it bonds. Now, in order to form this molecule at 120, we need 3 equivalent orbitals. Okay, so you can say, first I forgot, on the last example I forgot to show you, you can promote this. I don't know if that's really what happens, right? It doesn't even matter. You don't even have to draw these electrons in. That's not really important right now. What's important is that you recognize you need 3 orbitals that are identical to each other. Not a ball and 3 sticks stuck at 90 degrees from each other. Okay, if you need 3 equivalent orbitals, you need to put in your blender 3 orbitals. Right? So we're going to put 1 of the S's and 2 of the P's, blend them up, and now the blender will spit out 3 identical orbitals. And since these 3 were made from 1 of the S's and 2 of the P's, these are each called sp2 hybrid orbitals. Now, this one was untouched. We never put that in the blender. It was never mixed. It was never hybridized. That's just called your unhybridized p orbital. Okay, now let's go make this molecule. Now that we have 3 equivalent orbitals. All right, so the carbon on the left. All right, you have your Lewis structure. Hope you copy this down, because I'm gonna just keep scrolling it out of the screen. That carbon on the left looks like this. It's got 3 of these sp2 orbitals that are mixed up, not mixed up, hybridized. So they're all equivalent, and then you have an unhybridized p orbital. You have the same thing right next to it. The carbon on the right is just the same as the carbon on the left. Hybridization terms. All right, now we can put those electrons in. So it didn't matter you promote it or what. The first thing is you just get the number of orbitals you need. I'm going to do the hydrogens in blue again. Right, I'll just put 2 on either side. All right, I'm going to try to draw this 3D for you just like I did in class. There's the carbon, nucleus. All right, this here is going to form a sigma bond with that. All right, so there's my sp2 orbital. There's my sp2 orbital. They're going to bond straight ahead. So this is the sigma bond. Right, that's up here. That's one of these things. Next, we'll draw that one. This one's 120 degrees now. 120. Now we can do this because there are all 3 of these sp2 orbitals look exactly the same. All right, there's an electron in there. That's going to form a bond with this guy, that hydrogen, there's another sigma bond. Right? So that one just bonded with that. Right? So that's this here maybe. All right, let's do this one. 120. It's got an electron in there. Oh, sorry, let me make that all these carbon electrons black. All right, we're doing that one now. All right, that one is going to bond with that one. They're going to bond now. All right, so here comes that hydrogen. There's another sigma bond. All right, so all these here, overlapping the red, those are the bonds we just drew. We drew three sigma bonds. All right, let's go to the carbon on the right. I'm going to do that one, bonding with that one. Right, let's put that here. 120. There's carbon's electron, and here's hydrogen. All right, and here we go. There's that one, the last sp2, and there's that electron, and here comes that hydrogen now. Hydrogen comes in an s orbital, the electron does. There it is. And we just did our last two sigma bonds. So this molecule has 5 sigma bonds. Now let's draw this here. This is the pi bond. It's going to be side to side overlap. These are all head to head. Now remember, this hybridization scheme leaves one p that was never put in the blender. It's unhybridized. It just looks like a regular p orbital. Looks like that. Now once they get close enough, they're going to feel that attraction, and they're going to overlap side to side. Right, so there they are. And once they feel that attraction, they're going to overlap side to side here. Side to side. Right, so this is one orbital, not two. So we can put 2 electrons in any kind of orbital, atomic or molecular. So there it is. Let's recap. If you need bond angles of 120 degrees, the hybridization in this model has to be sp2. You need to mix 1s with 2 p's to get 3 equivalent orbitals to make bond angles of 120. Last scenario we considered was C2H2, ethyne. Step 1, draw the Lewis structure. If you draw the Lewis structure, you get this. Step 2, use VSEPR. All right, we'll pick one of these carbons. They're both the same. Or they're both the same hybridization. Right? So determine the number of electron domains. There's 2. All those 6 electrons in that triple bond, they're not independent of each other. They can't separate from each other. That's one area of electron density, and that's another one. When you have 2 areas of electron density, this is a linear geometry. It's 180 degrees. That's going to tell us the hybridization. If we need 2 bonds, that's what we need to get 180. All right, only if you have 2 bonds can you get maximum separation of 180. If you have 3 bonds, you get 120. If you get 4 bonds, you get 109. So reality tells us this molecule has a 180 degree bond angle. Therefore, it must have 2 equal bonds. Therefore, the hybridization must mean whatever we put in the mixer has to spit out 2 equal things. So here we go. Before this carbon is hybridized, I'm going to go through this a little bit faster now. It has 2 electrons in its 2s and 2 electrons in its 2p. Okay, now you can promote this guy and you can do that if that helps. But the bottom line is we need to put something in our blender, and that blender, hybridization is what it's called, needs to spit out 2 equal things, orbitals. That way we can put one pointing that way, the one pointing the other way, and get this bond angle, 180 degrees. Alright, so if we want 2 orbitals that are identical to each other, we need to put 2 atomic orbitals into this hybridization mixer. Therefore, these two resulting hybrid orbitals are called sp hybrid orbitals because you put one s and one p into the blender. Now these two were unhybridized. They're untouched. They're just your regular px and py orbitals. Right. Let's use this scheme to now describe the two carbons in this molecule. All right. Here are your sp orbitals for the carbon on the left. Here are your two untouched p orbitals. Carbon on the right, here are your sp orbitals, and here are your two untouched p orbitals. There's a hydrogen, I'll put one on the left, and there's a hydrogen, I'll put one on the right, just to balance it out. All right, before I forget, let's give these carbons, which are now hybridized, it's 4 valence electrons. Let's get to work. This thing is going to bond, overlap with that sp orbital. This and that. That's going to be a sigma bond. All right, let's draw that. Here's my nucleus. Here's my nucleus. Do that a little better. Getting a little sloppy now. All right, so there's the sp. There's an sp. There's a sigma bond. There's only there's only one more left. That's why it can go 180 degrees. That's going to overlap with this hydrogen. Hydrogen is on its way. Make that sigma bond there. That direct head-to-head overlap. Okay, we're done with the left. Now let's work on this one. That one's there. It's got an electron, and this hydrogen is on its way. Okay, all the sigma bonds are taken care of. So up here we just did that sigma bond, that sigma bond, that sigma bond. All right, so by the way, every single bond is a sigma bond. Every first bond in a multiple bond is also a sigma bond. Now let's take care of the unhybridized p orbitals. The p orbitals we never put into the blender. All right, I'm just calling it a blender, but it's called hybridization. All right, let's take a look at this one here and that one there. All right, let's say one. I'm gonna have to slightly angle this off because I'm drawing on a flat screen. But these p orbitals are 90 degrees from each other. All right, there's one right there, orange, and here's the other one on that carbon on the right. Now they're going to feel that attraction to each other, and they're going to overlap. All right, so let me see if I can do that. All right, so they're going to feel that attraction, and they're going to overlap side to side. So side to side overlapping and forming bonds. That's called your p, or that's called your pi orbital, pi bonds. I'm sorry, pi bonds caused by p orbitals overlapping. All right, so again, max 2 electrons, top and bottom. That's all one bond. Now let's go to see if we can see this. Try all this here. This one is this p. All right, perpendicular to the orange one I just drew. That one, that one. All right. So here we just did one of these. Now we're going to do this one here. Pi bond here, pi bond there. All right, now you know these guys are going to be attracted. They're going to feel that attraction too, this way. All right. Here we go. Attraction there, attraction there, attraction there, attraction there. All right, and then 2 electrons in those as well. Let's go that one. All right, so it got super messy, but that's really what I'm drawing here is there, sigma bond, sigma bond, sigma bond. There's your H, and then you have a pi bond and then pi bond. All right, so just to recap, if you need 180 degrees, so both these carbons need 180 degree bond angles around them, then you need 2 equivalent orbitals to do that. So the answer is going to be sp3 hybridization. Quick recap of all the 3. If you need tetrahedral, so you got to determine this from VSEPR and Lewis. Tetrahedral, right? In other words, 109 angles. The answer is going to be we need sp3 hybridization. If you need trigonal planar, geometry around the central atom, in other words 120-degree bond angles, the answer is sp2. All right, because you need to mix one s and two p's to get 3 equivalent orbitals to make 3 equivalent bonds. All right, and the last scenario is if you determine that you need a linear geometry around the central atom, in other words 180 degrees, the answer is sp hybridization. Good luck.